Hi everyone, and welcome back. And now we've sort of built up and talked a little bit about circuits, but we want to maybe lay some ground rules first and talk about some of the other basic quantities and electrical components. So we're going to talk about current, we're going to talk about resistors, and a few other basic things. And so to start off, let's draw one of the most basic circuits that we can. It essentially represents a lot of the other circuits we have around the home. And that's, we have some type of voltage source. That could be a battery, that could be energy created from a power plant miles away, traveling all the way to our house. But here we have one component that we're going to be introducing now. It's called a resistor, and all essentially a resistor does is resist in a circuit. You have electrons passing through it, and it doesn't like that and takes away some of the energy. So another basic concept we want to talk about is current. And so current, usually represented as an I, measures how much charge is passing through a point over time. So that you have some current passing over a resistor, you have some charges moving through it. It doesn't like that, it resists it, it takes some of the energy away from it. And so resistors are really helpful. A lot of the electrical components and appliances around our house are made of resistors, but I think one of the most basic and one of the most interesting ones is a toaster. Turn on a toaster, you'll notice you have all these wires inside that are glowing red. So those are resistors. In fact, it's really just one wire wrapped around that's being heated, but it's wrapped around so it heats the toast and bagels on all different sides. But essentially what it's doing is taking the electrical energy, the current passing through them, and changing it into heat. That's all resistors do. And you can imagine why that'd be helpful in a lot of different circumstances, like heating up toast, or maybe heating up food, or even having a space heater heating up your room. So resistors play a pivotal role in a lot of the appliances we have running around, but also just in basic circuitry and electronics. So let's take another deep dive what's going on inside that wire instead of really inside any wire. So you have charges moving, and this time we'll assume positive charges. When we talk about a direction of current, charges are moving direction, we talk the direction that positive charges are going, but in reality we know that's really the electrons are the free ones, so the electrons would really just be going the opposite direction. But we have a current, we create a little cross-sectional area, and we count the number of charges passing through, that's this change in Q, over a change in time. So we might find it's useful sometimes to write this out in terms of this expression, but you have the particle density, so the number per volume or meter cubed, the charges of this, and usually it's going to be things like charged electron, that's typically what's passing through here. The drift velocity, so it essentially represents the total bulk velocity of these electrons moving, and this A, this cross-sectional area that we cut out of this wire. Charges are really bouncing around and doing crazy things. So this drift velocity is really describing the bulk motion as it's moving to the side. It's just overall going to have some velocity when we count up all the electrons and how they're moving over time. So let's do a quick problem with that equation. So we have a copper wire here. It is a cylinder, which means that its cross section is a circle. So we're told the particle density, and these are going to be electrons. We're told the radius of this cylinder, and we're told the amount of current passing through. So we want to find the drift velocity. How fast are these electrons moving in it? So we can expand out and write that equation that we just talked about. So the current equals the charge density, charge, drift velocity, cross-sectional area. So we're going to want to solve for this bit. So the cross-sectional area of a cylinder is a circle. The area of a circle is pi r squared. We're given the radius of that there, so that's fine. So we can take all that stuff that's not this drift velocity, move it to the other side, divide it out, so we get this expression, and we'll find that the electrons really aren't moving that fast. I mean, that's 10 to the negative 5 meters per second. That's much slower than how we move every day. A pretty fast sprinter is moving in tens of meters per second. But we walk around with something be like a meter per second. This is really slow, but remember there's a lot of electrons doing this. There's 10 to the 29 per meter cubed. So likely there's something like 10 to the 20 crammed in this little wire here. So overall the effect does matter. There is some type of bulk velocity. It's just a lot of electrons doing that. They're all bouncing around, but they're generally moving together in one direction. So we want to repeat the same thing with aluminum, so it has a different number density. We put that in, we get a slightly slower speed. So we typically use copper because of a lot of different reasons in wire. Well, it's not that it's the best conductor, it's pretty close to one of the best conductors, but it's also very cheap. But the other things like aluminum maybe don't do as well. It doesn't move as fast and maybe not as efficient. So we're going to do a little bit of a math problem here, just sort of showing a property. So we're going to assume a property here. This is actually really important. We should have we should have started and introduced it, but this is something we're going to be using for a long time. So it's a really important property. It's called Ohm's law. In fact, we'll likely be using this for a number of videos after this. It's a pretty important property. So it's saying for resistors, so imagine I have a resistor here. It's saying the change in voltage over it. So again, that resistor takes away some type of voltage. That's what's being represented here. There's some current, there's some amount of charges passing over it. And has some resistance, so that's inherently how good is it at resisting all these charges moving through. That's what this R means. So the change in voltage is going to be the current times this resistance. So you can think of this as something that's analogous to the Q equals V relationship we had for capacitors. So, another basic relationship for the three fundamental things to do with this component. So with that relation, we want to say something about the electric field going on these wires. So we have moving charges, so we have charges going on, so there's got to be some type of electric field that's pushing them forward. So we're going to claim it's the current density, so the current per area, times the charge density, the charge per volume. You do want to be part of the video, but no, don't eat the plant. So we're going to throw in a few more relationships we should probably know and then probably should talk about, but so we talked about before that the change in voltage is going to equal the electric field, negative electric field, times a change in distance along some line of sight. And so also going to claim another equation, so we can write the basic resistivity of a wire is equal to this interesting little constant here. It's something. Do you want to be part of the video or not? Something this resistivity times distance. This is something that's inherent to a substance like aluminum or copper. So it's something you can always look up, times the change in distance. So this is going to be the length of the wire times this cross-sectional area. Again, if we cut out a little section here. So we're starting off here with Ohm's law. So we can rewrite that in terms of the electric field and this change in distance with this property that we pulled. So we can rewrite the resistance in terms of this equation that we just used up here. I just realized I said that this was the charge per volume. It's actually the resistivity, so ignore that part in the beginning video. So we go and get rid of the change in distance because it appears on both sides. So we're just left with this stuff on the right side. So we get the electric field equal this stuff. We notice that we define the current density as the current per some cross-sectional area. That's exactly what we have here. So we get the current density times this resistivity. So let's do another problem. And the nice thing about a lot of these problems is they have a lot of direct real-life applications. So we have a kettle here. It has it's being heated by some resistor. It's giving it heat. And we want to say a few things about it. We want to say what's the power of this resistor, this setup, and how long is it going to take to heat up, and how much is it going to cost to do that. So another relationship we're just shoving in and just going to claim is true moving forward is going to be the power over resistor equals the current times the voltage. So this P equals IV thing is somewhat analogous when we talked about the energy being held in a capacitor. It's looks something like this, 1/2 QV. So I want to ask, what's the power of the heater in this situation? We have the heat capacity. We have the heat capacity of water. We have as much, 1 kilogram of water. We have a 2 ohm resistor. We have a 12 volt battery. What's the power of a heater? What's IV? So we don't actually know the current in this situation. We actually only know the voltage and resistance. So thankfully with Ohm's law, we can go and substitute that in and solve for I. So I equals V over R. We go use that, put it in here, so we get V squared over R. So we find that 72 watts, and that's not a ton of power, but we'll see how long it takes. So how long does it take to heat this water from 20 degrees Celsius to 50 degrees Celsius? Mind you, 50 degrees is kind of lukewarm. It's boiling as 100 degrees Celsius. This is about room temperature. So how long is that going to take with this little resistor? So recall that the power is the change in energy over the change in time. So we're going to write this change in energy as MC change in T. So this is the change in its thermal energy over time. So here we have the mass, we have this like specific heat, and this is something like energy per mass per temperature. So, and then the change in temperature that it's going to experience can go from 20 to 50. And we want to find how long it takes. We can go and solve for this time. We multiply to the other side. We divide P out to the other side. Here we go. We get this change in energy over the power it is. So we find it's 1700 seconds, which is 30 minutes. That's a really, really long time to get from room temperature water to lukewarm water. So thankfully, we normally use much higher power things, the heaters in this, like for a kettle or, for a coffee heater, you use a lot, pretty high powered thing, and you just use it for a little bit. So you can go and bring something from roughly room temperature to boiling in just a matter of a few minutes, but it does take a lot of energy. But it's just a lot of energy for a very little amount of time. Overall, it's about the same amount of energy anyway. And another reason why this is not a good idea to use this setup in this low of power is that it's gonna lose a lot of heat, in this time. So we're assuming it's not losing any heat from any other way, and there's gonna be some subtractive term here because, when something gets hot, it does emit heat compared to the surroundings. Dude, that's why we generally wanna do this quickly and not, take 30 minutes, because you will lose overall less heat that way. Last question. So we're gonna assume a cost for electricity, and that's something I looked up for my local area. Well, I looked it up a year ago, so maybe it's actually changed in price, but it's about, 13, 14 cents per kilowatt hour. So how much does this actually cost to heat up this water? So we go and we put the energy it takes. So it kind of looks weird, but a kilowatt hour is actually a unit of energy. It's a watt hour, so watts energy per time times a time. So it is energy. We go and put in the energy that it took 1.26 times 10 to the 5 joules. It takes, not even a penny. So not very expensive, and generally why it's usually pretty inexpensive to cook and heat things and, create coffee, for instance, in your own home, because the water is very cheap and the energy is relatively cheap. But again, we would probably use something that's a little bit higher energy, and we probably want to go up to boiling. So maybe, double that one thing. So going to cost us a whole cents to heat up that kilogram. I mean, we're really breaking the bank. So but let's keep going with this cost thing. I just wanted to add this in because I think it's a good thing to have a perspective. I always had, raised in a household, and I had roommates that are complaining about, oh man, you can't leave that light on, you can't leave that space heater on, it costs so much. So how much does it actually take to run some of these things? Because I have a space heater going right now. It's going to be a high of 5 degrees tomorrow in lovely Midwest. But how much is actually going to be costing me, say like a month, to run this space heater? Is it really going to be breaking the bank? Let's go figure that out. So roughly, the cost is going to be the cost per energy times the power times the time. So most things you can figure out their power pretty easily. The cost per energy is something that your power company just straight up tells you, and something you want to input is going to be the time it takes. Because sometimes you have something that's running all the time. Maybe you keep your space heater on all the time, or a fan all the time, or maybe you just have a microwave and use it for max 5 minutes a day. So one of the interesting comparisons we can do off the bat is compared an old-fashioned or incandescent light bulb to an LED one. And so these basically are just essentially throwing a resistor inside this, almost vacuum-like state and letting it up, making it, pretty high temperature compared to just an LED, which is making very specific frequencies of light. So there's been a huge increase of efficiency going from one to the other. So where does this come from? Well, it has to do with the fact that this incandescent bulb is a black body. So imagine this is light frequencies, this is the energy at them. And so this light bulb looks something like this. So maybe this is all of the visible light here. You'll find that most of the energy is actually going to something called infrared. So it's lower energy light than visible light, but we can sort of feel it as heat. So a lot of the energy that you put into an incandescent light bulb, it just goes straight into heat. It's actually not useful as a light bulb. So what people figured out with LEDs is that if we actually just make something that creates mostly light in this visible spectrum, actually that's what we want a light bulb to do, see things, that it's much more efficient. So that's essentially what happened. So we can compare something that's 100 watts towards a 100 watt equivalent 12 watt LED bulb, and consider it can be something like 8 times more efficient. So if we left on this light bulb all the time, so something my mom complains about me doing, it would take $10 a month to light that light bulb if it was a traditional incandescent one. So if you just take that and replace it with one LED light bulb, you essentially only be paying 1/8 the price. So even if you leave on a light bulb all the time, it only costs about a little over $1 to run if it's an LED. So maybe you don't have to worry so much about leaving the lights on. Maybe you want to save that $1. I don't know, it's up to you. You can see how much incentive there is to use LED light bulbs, not only for energy efficiency and environmental stuff, but just personal cost savings. So another thing we could do is compare something like a fridge or a personal heater. So a fridge actually uses a lot of power. So 780 watts. So if this ran continuously all the time, it would cost an eye-watering $77 a month. So thankfully, fridges don't actually run all the time. The point is that they're very efficient and that they don't let in heat. So how a fridge works, essentially, it's a heat pump. It pumps heat out of it and tries to keep it out by having really thick insulation. So if you notice, as you sit by your fridge, it actually doesn't run all the time. It runs actually pretty infrequently, just as a little more heat is crept in, below some tolerance level. Then it kicks it out. So this is, in reality, is actually much lower than this. And you can do comparisons to, microwaves are like 1,000 watts. So it'd be like $100 to run this per month, but you don't run a microwave continuously. You just run it for 5 minutes a day or whatever you need. So here's the big question for me that I was talking to my roommate about, because he would say, oh, it costs $50 a month to run a personal heater. Yeah, but only if you run it continuously. Maybe you only use it for nighttime, like 1/3 of the day. So it'd be 1/3 of the cost here. Maybe you actually have one that has a thermometer on it. So if it gets too hot, it turns off. It's only, intermittently turns on. So this could actually be pretty low, something like $5, $10 with the proper usage. Okay, everyone, thanks for joining me. I hope you learned a lot. I think there's a lot of things that we can glean from some of the sections and types of physics we're getting to now. So hopefully you got something from that. Let me know how it went. Thanks for joining me. Okay,